It is January 26, 2026. And what just happened over North America is something scientists will question in the history book. You see, in January 1985, America froze. The kind of cold that breaks records, shatters infrastructure, and becomes a generational memory. Meteorologists called it the ghost year. It was supposed to be a once-in-a-lifetime event. But right now, over North America, something is assembling that is making forecasters pull up those 40-year-old records and realize they might fall. This isn't a typical winter storm. It's what scientists are quietly calling a systemic atmospheric collapse. A superarctic blast where moisture, cold, and terrain are combining into a configuration that produces ice, not snow. The kind of ice that doesn't melt, that entombs entire regions, that breaks infrastructure designed for normal winters. And the pattern is repeating, reloading in ways that suggest we've entered an entirely new regime. Stay until the end to discover what's really happening above your head. If this has you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. This is not a storm that's forming. It already snapped into place. Right now, while you're reading this, the atmosphere over North America is behaving like a machine that's already jammed, not a storm system organizing itself, not weather evolving through predictable phases. We're watching a systemic atmospheric collapse happening in real time. And the terrifying part is that the failure signature was written into the data days ago. The professionals saw it. They just didn't want to say it out loud yet. You've probably heard the term superarctic blast thrown around in weather headlines. Forecasters love their dramatic labels, but that phrase, as alarming as it sounds, actually understates what matters here. We're not just talking about cold air moving south. We're talking about the atmospheric configuration that creates entombment. Not just a cold snap. The ice component, the persistence factor, the reloading mechanism. These are the elements that separate a memorable winter event from something that dismantles infrastructure and strands populations for days or weeks. The elite weather audiences, the people who track models obsessively, who understand ensemble spreads and know the difference between deterministic runs and probabilistic forecasts. They've been watching something unsettling develop. The models aren't converging, they're fragmenting. And that matters because in normal storm forecasting, as you approach the event window, uncertainty should shrink. The various computer models should start agreeing with each other. The cone of possibilities should narrow. But that's not happening here. Instead, we're seeing what meteorologists call ensemble spread widening near impact time. The European model and the American model are telling different stories. The individual ensemble members, the slightly varied runs of the same model, they're scattering across a range of outcomes rather than clustering together. When uncertainty grows as the storm approaches, that's a bad sign. It means the atmosphere is in a sensitive state where tiny differences in initial conditions produce wildly different results. It means we're dealing with something that doesn't fit neatly into the pattern library that these models were trained on. Let me explain what entombment means in practical terms, because this isn't about snow depth records or which city gets the most accumulation. Entombment is about immobility. It's about roads that aren't just covered, but glazed with a layer of ice so smooth and persistent that salt doesn't work and plows can't grip. It's about power lines accumulating weight until the physics of tension and brittleness take over. It's about recovery operations that can't begin because the people who would perform them can't reach the equipment, and the equipment can't reach the damage. Snow is visible. Snow looks dramatic on camera, but ice is the quiet killer. Ice is what turns a winter storm into a multi-week infrastructure nightmare. The historical benchmark everyone keeps mentioning is January 1985. If you talk to meteorologists who were working back then, or if you dig through the archives of record cold outbreaks in the United States, 1985 is the ghost year. It's the folklore reference point. That month produced record-breaking cold across enormous swaths of the country. Temperatures that hadn't been seen in a century of record-keeping, agricultural losses, infrastructure failures, the kind of cold that becomes a generational memory. And here's the thing nobody wants to acknowledge yet. Multiple indicators suggest we're approaching or potentially exceeding anomaly magnitudes comparable to that event. Temperature departures 40 to 45 degree below normal. That's not a weather statistic. That's a structural signal that systems designed to operate within a normal range are about to be stressed beyond their tolerances. People will argue about inches of snow. They'll debate whether their city will see 6 inches or 12. They'll track the snow terrain line like it's the only thing that matters. Meanwhile, the real threat is invisible. It's the warm layer aloft that melts the snow into rain, and the sub-freezing surface layer that instantly refreezes that rain into glaze ice. It's the moisture content in the air that nobody sees until it's coating every exposed surface with a crystalline shell. You want to know the scariest part? The models that are supposed to forecast precipitation amounts, they're notoriously bad at handling the specific atmospheric profile we're dealing with here. The combination of an atmospheric river, which is essentially a corridor of tropical moisture being transported thousands of miles, colliding with air masses that are behaving like they belong in the Arctic. This creates humidity profiles and precipitation rates that fall outside the normal parameter space, which means the quantitative precipitation forecasts, the QPF numbers that emergency managers use to plan responses, those numbers might be conservative. They might be underestimating what's coming because the moisture isn't acting like moisture should. And that's where things get really strange. This is a river of tropical moisture meeting air that behaves like liquid nitrogen. Atmospheric rivers are real meteorological phenomena. They're not some fringe concept or conspiracy theory. They're long, narrow corridors in the atmosphere that transport enormous volumes of water vapor, sometimes carrying more water than the Amazon River at any given moment. Most people associate them with West Coast flooding events, those Pineapple Express storms that drench California and Oregon. But atmospheric rivers aren't confined to one coast. They're features of the global circulation. And when the jet stream gets contorted into the right configuration, these moisture plumes can redirect into major cyclones anywhere. What's happening right now involves not one but two moisture waves converging. There's a subtropical Pacific feed pulling moisture from near Hawaii, and there's a Gulf of Mexico feed pulling warmth and humidity from the Gulf. And these two streams are merging into a developing nor'easter system. This is the conveyor belt mechanism that meteorologists talk about when they're trying to explain why some storms are different. The moisture doesn't arrive as a single pulse. It keeps feeding. It reloads. This turns what would be a normal winter storm, maybe 6 to 12 hours of precipitation, into a multi-day reload loop where wave after wave of moisture keeps slamming into the same region. Now, here's the critical misunderstanding that's going to dominate the conversation and completely miss the point. People are going to obsess over the rain versus snow line. They're going to watch radar and argue about whether their area will see rain or snow, but that's the wrong binary. The real question, the one that determines whether this is a manageable event or a catastrophic one, is about the vertical temperature profile. When you have a warm layer aloft several thousand feet up in the atmosphere, and you have a sub-freezing layer at the surface, you create the conditions for extended freezing rain. The snow that forms in the clouds falls through the warm layer and melts into rain. Then that rain falls through the sub-freezing surface layer and instantly freezes on contact with anything: roads, trees, power lines, vehicles, buildings. This is how you get ice accretion in fractions of an inch that can down thousands of trees and collapse power grids. The physics here are straightforward, but the execution is diabolical. Cold air is denser than warm air. It's heavy. It sinks and pools at the surface. Warm air, being lighter, rides over the top of it. So you get this stratified atmosphere where warm, moist air is streaming northward at mid-levels, but at the surface, you have this stubborn dome of sub-freezing air that refuses to move. The Appalachian Mountains act like a dam trapping the cold air against their eastern slopes. This is called cold air damming, and we'll get to that mechanism in detail later, but for now, just understand that this setup creates an extended freezing rain zone that can persist for days. Imagine driving down a road that looks wet, just wet, maybe a little shiny. You're going normal speed because it doesn't look dangerous. Then your tires hit that surface and you realize there's no friction. None. You're on a skating rink at 45 mph, and your brain doesn't have time to process what's happening before you're in the ditch or into oncoming traffic. That's what freezing rain does. It looks normal. It looks like rain, but it's a transparent coating of solid ice. Now scale that up to an entire region, millions of people, Thousands of miles of roads, hundreds of thousands of miles of power lines. Trees that are already stressed from previous storms, now accumulating a quarter inch, a half inch, an inch of ice on every branch. The weight doesn't sound like much until you do the math. Ice is heavy. A large tree with a full ice coating can be carrying thousands of pounds of extra weight. Branches snap, trees fall, and when they fall onto power lines, the lines don't just break cleanly. They snap under tension, transformers blow, substations go offline, and because the roads are impossible, the repair crews can't get to the damage. This is why freezing rain is worse than snow for infrastructure. Snow is plowable, snow is manageable. Freezing rain is a cascading failure mechanism, and here's the psychological component that makes it even more dangerous. Snow looks scary. When people see snow in the forecast, they prepare. They stock up, they cancel plans. But when they see rain in the forecast, even if it says freezing rain, their brains don't process the threat the same way. Rain looks normal. Rain doesn't look like an emergency. So people go about their business until suddenly they can't, and by then it's too late to prepare. The National Weather Service knows this. The forecasters who are issuing the ice storm warnings, they're using language like catastrophic ice accretion and infrastructure damaging ice because they need to break through the psychological barrier. They need people to understand that this isn't rain. This is a weapon that the atmosphere is deploying against every exposed surface. And the moisture that's feeding this weapon, it's coming from a tropical source, thousands of miles away, being channeled northward by the jet stream, which has been contorted into a shape that shouldn't be stable, but somehow is. The atmospheric river is locked in. The cold dome is locked in. And they're colliding right over the most populated corridor of the eastern United States. But here's the part that should really disturb you. The cold air isn't just sitting there, it's being replenished, it's reloading. And the source of that cold air, the polar vortex itself, didn't just wobble or displace the way it normally does. It fragmented, it weaponized itself. And that's a story that goes way beyond normal weather patterns. The polar vortex didn't move, it multiplied. You've heard the term polar vortex thrown around every winter for the past decade. It became a meme. It became shorthand for really cold weather. But the actual polar vortex, the meteorological phenomenon that scientists are referring to, is a specific thing. It's a large area of low pressure and extremely cold air that sits over the polar regions, particularly strong in winter. It's not just cold air, it's a circulation pattern, a vortex of strong winds in the stratosphere, miles above the surface, that normally keeps the coldest air bottled up near the poles. When the polar vortex is strong and stable, the cold stays put. The jet stream, which is essentially the boundary between cold polar air and warmer mid-latitude air, maintains a relatively circular path around the pole. But when the vortex weakens or gets disrupted, it can send lobes of Arctic air plunging southward into mid-latitudes. These are the polar vortex outbreaks that make headlines. What's happening now isn't a simple displacement. It's fragmentation. Think of it like a spinning top that's cracking into pieces, but the pieces are still rotating. The vortex is split into multiple lobes, multiple centers of circulation, and each lobe is capable of pushing extreme cold into different regions. This is what meteorologists mean when they talk about a disrupted or fragmented polar vortex. It's not one coherent circulation anymore. It's multiple semi-independent circulation centers, each one acting like a pump pushing Arctic air southward. The terrifying implication is what some are calling the pendulum swing pattern. Instead of one big Arctic outbreak followed by a gradual moderation, you get repeated blasts. The first lobe swings through and delivers extreme cold. Then it retreats, but it doesn't dissipate. It reloads. Another lobe swings through, then another. The atmosphere doesn't reset to normal between events. It oscillates between extreme cold and slightly less extreme cold, never returning to what we'd consider a normal winter pattern. And here's where the fear comes from among meteorologists who've been watching this develop. After one major Arctic outbreak, the system shouldn't be able to recharge this fast. The cold pool should moderate, the jet stream should relax. But what the models are showing and what the observations are confirming is that the cold pools over Canada are replenishing faster than normal. New surges of Arctic air are dropping down from the high latitudes to replace what was just exported southward. It's like the atmosphere has found a conveyor belt configuration that keeps delivering fresh Arctic air to the staging areas, ready for the next southward push. The public got misled over the years because polar vortex became a casual phrase. Every cold snap got labeled a polar vortex event. But the actual mechanics, the stratospheric disruption, the lobe fragmentation, the reloading pattern, these are serious atmospheric dynamics that don't happen every winter. There's a phenomenon called sudden stratospheric warming that can act as an upstream trigger for these events. This is when the stratosphere, that layer of atmosphere miles above where weather happens, experiences a rapid temperature increase. This might sound backward. Why would warming in the stratosphere cause cold at the surface? But the warming disrupts the circulation. It weakens or splits the polar vortex. And when the vortex gets disrupted in the stratosphere, the effects can propagate downward over the course of weeks, increasing the likelihood of Arctic outbreaks at the surface. Now, let me be clear about what's confirmed versus what's speculative here. The polar vortex exists. That's not debatable. Arctic outbreaks happen. That's normal winter weather. What's unusual is the fragmentation pattern, the reloading speed, and the apparent lock-in of a circulation configuration that keeps pumping cold air southward instead of allowing the pattern to break down. There's a speculative angle that I need to mention, clearly labeled as speculation, that if you were trying to destabilize infrastructure, if you were attempting to stress test societal resilience, you wouldn't want one clean storm. You'd want repeated waves. You'd want the first event to damage systems and then the second event to hit before repairs are complete. You'd want the cold to reload faster than the recovery effort can mobilize. The fact that the atmosphere appears to be doing exactly this, whether through natural variability or some other mechanism, is what's feeding the sense of wrongness that weather watchers are feeling. The lobe pattern makes the atmosphere behave like a repeating shockwave. One blast hits, systems struggle to recover, another blast hits, and the signature in the data, the temperature anomalies, the geopotential height fields, the vorticity maps, they all show a coherent pattern that doesn't look random. It looks organized. It looks like something that's locked into a groove. And when you see temperature anomalies of 45 degrees Dow below normal showing up in the forecast maps, you're not looking at weather anymore. You're looking at something else entirely. People obsess over absolute temperature. Professionals watch anomalies. If I told you it's going to be 20 degrees F, your reaction depends entirely on context. 20 degrees F in Miami is catastrophic. 20 degrees F in Minneapolis in January is a mild day. The absolute number doesn't tell you anything about significance. But if I tell you that temperatures are running 45 degrees below the seasonal average, that tells you everything. That tells you that whatever systems, natural or built, are adapted to operate within the normal range, they're about to be stressed far outside their tolerances. An anomaly is simply the deviation from the baseline. If the normal high temperature for late January in a given location is 40 degrees F and the forecast is calling for 5, you have a 45 degree negative anomaly. That's the language meteorologists use to identify extreme events because it removes the geographic context and focuses on the departure from what's expected. Why does this matter more than the raw temperature? Because everything is designed for the normal range. Power grids are designed to handle typical winter loads. Road salt is stockpiled based on average winter severity. Building codes assume certain temperature minimums. Agricultural systems assume certain frost dates. When you push 45 degrees outside that normal band, you're in a regime where failures start cascading because nothing was built to handle it. The detail that's buried in the forecast discussions, the technical language that meteorologists use in their internal communications is terrifying when you parse it. They're seeing cold pool temperatures approaching 40 degrees Celsius. Not just at the surface, but at the mid-troposphere level, around 18,000 feet up. This is what's called a full column cold outbreak. The cold isn't just a shallow surface feature. It extends vertically through the entire lower atmosphere. This matters because precipitation mechanisms depend on the thermal structure of the atmosphere. When you have deep pervasive cold, it supports stronger winter weather processes. It means snow growth is efficient. It means ice accretion is persistent. It means the atmosphere is primed to squeeze every bit of available moisture into frozen precipitation. Here's a metaphor that might help. Imagine spilling cold water on a table. It spreads out, but it's shallow. You can mop it up. Now, imagine flooding the entire room. The water isn't just on the surface anymore. It's everywhere. It's soaked into the walls. That's the difference between a surface cold snap and a full column cold occupation. The cold isn't just sitting on the ground. It's occupying the entire atmospheric volume. And it's not going to dissipate quickly because there's nowhere for it to go. The comparison to January 1985 keeps coming up, and it's worth understanding why that event is the benchmark. 1985 produced temperature anomalies and absolute cold records that are still referenced today. It's the event that meteorologists measure other cold outbreaks against. And when you start seeing forecast maps that show anomaly magnitudes comparable to or exceeding 1985, that's when the term vintage cold starts appearing in forecast discussions. Meteorologists rarely use that kind of language. They're trained to be measured, to avoid hype, to communicate uncertainty. When they start using phrases like vintage cold or record-threatening cold outbreak, it's because they're seeing signals in the data that match or exceed historical precedents. It's not exaggeration. It's pattern recognition based on decades of events. But here's the unsettling part. In the days before a major event, there's often a period of calm. The weather looks normal. People look at the current conditions and think maybe it's not going to be as bad as they said. Maybe the forecast was wrong. This is the quiet before impact. And it's dangerous because it creates complacency. People see a 40-degree day 2 days before the event and they convince themselves it's not coming. Then the cold arrives and it doesn't leave. The record threats develop fast once the anomalies cross certain thresholds. Temperature records are local and specific. Every city has its own historical minimum for a given date. But when you have a regional cold pool, this intense, this persistent, you start threatening records across hundreds of locations simultaneously. It's not about one city setting a record. It's about entire states potentially entering record cold territory at once. And through all of this, the thing that should bother you most isn't the absolute cold. It's not the specific temperature reading. It's the fact that this isn't primarily a snow story. The snow will fall. Yes, some areas will see significant accumulations, but the kill mechanism, the thing that's going to cause the most damage and create the most danger, isn't snow, it's ice. And we need to talk about what ice actually does when it arrives in these quantities. Snow scares people. Ice ends cities. I want you to understand the fundamental difference between snow disruption and ice collapse because this is where most people completely miss the actual threat. Snow is plowable. Snow piles up, it looks dramatic, it shuts down highways and cancels flights. But cities know how to deal with snow. You bring out the plows, you spread the salt, you wait for the sun to do its work. Snow is a logistics problem. Ice is a structural failure event. Ice sticks to everything it touches. Ice accumulates weight on power lines until they snap. Ice transforms roads into skating rinks that can't be cleared with plows. Ice persists long after the precipitation stops because temperatures stay below freezing, and there's no mechanical way to remove a quarter-inch glaze coating from 10,000 miles of power infrastructure. When meteorologists talk about ice, they're not talking about inconvenience. They're talking about collapse. The forecast amounts for this event should make your stomach drop. Texas is looking at a quarter to half an inch of ice accretion. The Deep South, areas that haven't seen ice storms like this in a generation, could see up to 1 inch of ice coating every exposed surface. 1 inch doesn't sound like much until you realize that a single inch of ice on a power line increases its weight by several hundred pounds per span. That's not a number I'm making up to scare you. That's physics. Ice weighs approximately 57 pounds per foot, and when it accumulates radially around a wire, the loading becomes catastrophic fast. Power companies design their systems to handle snow and wind, but ice combines the worst properties of both. It adds massive weight while also increasing the surface area exposed to wind, creating a leverage effect that snaps utility poles like toothpicks. Let me explain how freezing rain forms, because understanding the mechanism helps you grasp why this particular setup is so dangerous. Freezing rain requires a very specific temperature profile in the atmosphere. You need snow falling from clouds aloft, passing through a warm layer where it melts into liquid raindrops, then falling into a shallow layer of sub-freezing air at the surface where it instantly refreezes on contact. That warm layer is typically between 2,000 and 5,000 feet above the ground, sandwiched between cold air below and cold air above. The rain stays liquid during its fall through the sub-freezing surface layer because it doesn't have time to freeze in mid-air. But the moment it touches anything solid, a car, a tree branch, a power line, a road surface, it flash freezes into a coating of pure glaze ice. This is fundamentally different from sleet, where the droplets refreeze into ice pellets before hitting the ground. Freezing rain is liquid until the moment of impact, which means it can coat everything uniformly, creating a perfect shell of ice that's incredibly difficult to remove. The reason the southern zones are uniquely vulnerable is that their infrastructure simply isn't built for this. Northern states have systems designed to handle ice loading. Their power lines have different spacing. Their poles are reinforced. Their crews have de-icing equipment and protocols. The South doesn't invest in that infrastructure because events like this are supposed to happen once every 20 or 30 years, not multiple times per decade. When you combine infrastructure that's not rated for ice with a population that doesn't know how to drive in it, and emergency response systems that don't have the equipment to deal with it, you create the conditions for a cascading failure that can take weeks to fully resolve. The grid doesn't just fail in one place, it fails in a cascade. One line goes down, load redistributes to neighboring lines. Those lines become overloaded and fail, transformers blow, substations go offline, and suddenly you have entire regions without power in sub-freezing temperatures. The grid cascade narrative goes like this. Ice accumulates on lines, causing them to sag between poles. The sag increases wind loading and creates more leverage. Eventually, something snaps, either the line itself or the pole. When that happens, other lines have to carry the load, but they're already stressed by size. Transformers that were running at normal capacity suddenly have to handle surge loads they weren't designed for. They overheat, they fail. Meanwhile, trees that are coated in ice start losing branches. Those branches fall onto power lines that are already at their breaking point. Roads become impassable, which means repair crews can't reach the damaged sites. Even if they could reach them, they can't work safely in ongoing freezing rain and sub-zero wind chills. The repairs that would normally take hours end up taking days. The outages that would normally affect hundreds of customers end up affecting hundreds of thousands. And all of this happens while temperatures are so cold that homes without power become genuinely dangerous within hours, not days. Here's the invisible catastrophe angle that nobody talks about until it's too late. Freezing rain happens while temperatures don't look apocalyptic on paper. The air temperature might be 30 stuff. That doesn't sound like a disaster. People see 30 degrees and think, okay, it's cold, but it's not Arctic hellscape cold. But 30 degrees with freezing rain is far more dangerous than 10 degrees with snow. The ice accumulates slowly enough that people don't evacuate. They think they can wait it out. Then the power goes out. Then they realize their pipes are freezing. Then they realize they can't drive anywhere because the roads are sheets of ice. Then they realize the power company is saying it might be 3 to 5 days before restoration. Suddenly that 30-degree day becomes a survival situation, and nobody saw it coming because the temperature didn't sound scary enough. The cold air damming setup we'll explore more later is already in place, and it's making the surface layer of sub-freezing air incredibly stubborn. The Appalachian Mountains are acting like a dam, trapping cold air against their eastern slopes and preventing it from mixing out or moderating. That wedge of cold air is going to persist even as warm, moist air rides up and over it, creating the perfect conditions for prolonged freezing rain. This isn't a 6-hour event. This is potentially a multi-day icing event where accretion continues in waves as different moisture pulses move through. Every time the precipitation pauses, people think it's over. Then another wave comes through and adds another coating. Let me throw a what-if twist at you. And I want to be clear, this is speculation, but it's informed speculation based on how these events tend to verify. If the precipitation rates are undermodeled, and there's reason to think they might be given the atmospheric river moisture feed, the ice accretion could exceed the forecast amounts. Models have a hard time with precipitation rates in these hybrid setups where you're combining tropical moisture with Arctic temperatures. They tend to smooth out the extremes. If the actual precipitation rate is 50% higher than forecast, you're not talking about half an inch of ice. You're talking about 3/4 of an inch. At those loadings, you start seeing structural failures, not just in power infrastructure, but in buildings, metal roofs collapse, carports pancake, greenhouses implode under the weight. The fear with this event isn't the peak intensity at any one moment. It's the duration combined with the reload waves. One 12-hour freezing rain event is manageable if you know it's coming and you can prepare. But 3 separate 12-hour events over a span of 5 days, each adding another layer of ice, while temperatures never get above freezing to melt what's already there. That's when you transition from weather emergency to infrastructure catastrophe. The system doesn't get a chance to recover between waves. The damage accumulates, the fatigue accumulates, the grid gets weaker with each successive hit, not stronger. Now the question isn't what's happening, it's why it's behaving like it's programmed. A mountain range just became the most important object in America. Right now, the Appalachian Mountains are doing something they've done countless times throughout history. But this time, the consequences are going to be worse than usual because of everything else happening simultaneously. They're trapping cold air, not just holding it in place for a few hours, but wedging it against their eastern slopes in a configuration that meteorologists call cold air damming. And when you understand how this works, you realize why the icing forecast for the southeast is so terrifying. The mountains aren't just passively sitting there. They're actively creating a thermal prison that's going to keep sub-freezing air locked at the surface. Even while warmer air tries to push in from the south and west, cold air damming happens when dense cold air gets pushed southward along the eastern side of a mountain range and has nowhere to go. The air is cold, which makes it heavy, denser than the warmer air surrounding it. That cold air piles up against the mountains like water backing up behind a dam, hence the name. High pressure to the north keeps feeding more cold air into the system, maintaining the wedge even as other forces try to erode it. What you end up with is a shallow dome of sub-freezing air, sometimes only 2,000 or 3,000 feet thick, sitting stubbornly at the surface while completely different air masses exist just a few thousand feet overhead. This is one of the most well-studied phenomena in Appalachian meteorology, and it's also one of the most dangerous because it creates the perfect setup for prolonged freezing rain. The way it forms is almost elegant in its simplicity, which is part of what makes it so insidious. High pressure positioned over southeastern Canada or the northern Appalachian pushes cold air southward. The cold air, being dense, flows downhill and along the terrain, but when it hits the mountain barrier, it can't easily cross over. The western slopes of the Appalachians act like a wall. The cold air wedges itself against the eastern slopes and Piedmont regions, creating what meteorologists call the wedge. Meanwhile, weather systems approaching from the southwest bring warmer, moister air that rises up and over the cold dome. That warm air melts, falling snow into rain, but the rain then falls through the cold wedge and freezes on contact with the surface. The setup is self-reinforcing. The cold air damming prevents the warm air from mixing down to the surface, and the warm air keeps feeding moisture that produces more precipitation, which falls through the cold layer and creates more ice. This is why cold air damming is a freezing rain amplifier rather than just a cold air retention mechanism. It's not merely keeping things cold. It's creating the specific vertical temperature profile that maximizes ice accumulation. If the cold air at the surface was just slightly colder, you'd get sleet or snow instead of freezing rain. If it was slightly warmer, you'd get plain rain. But cold air damming tends to hold temperatures in that knife edge zone right around 30 to 32 degrees, which is exactly where freezing rain thrives. The warm air riding over the top melts the snow efficiently, but the surface stays just cold enough to refreeze everything instantly. It's the worst possible configuration, and it can persist for many hours or even days. Models have historically failed to predict cold air damming erosion accurately. They know it's going to happen. They can see the setup forming, but they consistently struggle with the timing of when the cold wedge finally breaks down. The physics at that boundary layer, where cold, dense air meets warm, moist air, involves turbulent mixing processes that are difficult to resolve at the resolution most models run. What typically happens is the models forecast the cold air damming to erode faster than it actually does, which means they under-forecast the duration of freezing rain. Forecasters who are familiar with the local terrain know to adjust for this, to add several hours to whatever the model says for how long the cold wedge will persist. But even with those adjustments, verification often shows the cold air hanging on longer than anyone predicted. That's the pattern to watch with this event. If the models are saying 12 hours of freezing rain, the actual duration might be 18 or 24. Cities like Atlanta, which most people don't associate with major winter weather disasters, get dragged into the danger zone when cold air damming extends unusually far south. The Appalachians run from Maine all the way down into Georgia, and the cold air damming effect can propagate along the entire chain. When high pressure is strong enough and positioned correctly, that cold wedge can push all the way down to the Gulf Coast states, bringing the freezing rain threat hundreds of miles south of where people would normally expect it. Atlanta sits right in the sweet spot for this. It's far enough east to be influenced by the Appalachian cold air damming, but far enough south that it gets targeted by moisture from Gulf and Atlantic sources. The result is a city that occasionally gets absolutely hammered by ice storms that shut down everything for days. Think about what's happening in physical terms. It's not a cold front sweeping through and then moving on. It's cold air being pinned like a hostage against a mountain range, while wave after wave of moisture rides over the top of it. The front isn't moving because it can't move. The terrain won't let it. So instead of a typical weather system that progresses from west to east and clears out, you get a stationary setup where the icing just continues as long as the moisture and the cold air damming both persist. That's the nightmare scenario, and that's exactly what's being forecast for this event. There's precedent for this. Major cold air damming ice storms have hit the region before, and they're remembered decades later. The January 1982 ice storm, the December 2002 event, the February 2014 storm that stranded people on highways overnight in Atlanta. Each one followed the same basic pattern. Cold air damming sets up, moisture arrives, freezing rain accumulates faster than anyone expected, infrastructure fails, and recovery takes over a week. The people who lived through those events don't forget them. They know what ice can do. But there's always a new generation of residents who've never experienced it, and they're the ones who don't prepare until it's too late. What makes this particular setup more concerning is that the cold air damming isn't happening in isolation. It's happening while the polar vortex is fragmented and feeding additional reinforcing shots of cold air from the north. Normally, cold air damming events eventually erode as the high pressure weakens or shifts position. But if you keep getting fresh infusions of Arctic air from the north, the wedge doesn't break down. It just keeps reloading. The warm air keeps trying to scour out the cold dome, but new cold air keeps replacing what gets mixed out. You end up with a battle zone at the surface that can persist for days instead of hours. The Appalachians just became a weapon in an atmospheric war that's about to destroy power grids and immobilize entire states. And behind it all, Canada keeps refilling the freezer. Cold usually spends itself. This cold regenerates. When Arctic air plunges south into the United States, the normal pattern is straightforward. The cold air mass crosses the border. It spreads across the interior. Temperatures drop. Maybe you get some snow or freezing rain depending on moisture availability. And then over the course of a few days, the cold air moderates. It mixes with warmer air. It gets displaced by the next weather system, and temperatures return toward normal. That's how it's supposed to work. The cold is a finite resource. It gets used up. But what meteorologists are seeing with this event is different. The cold pools over Canada aren't depleting the way they should. They're regenerating. They're reloading faster than the physics should allow, and nobody has a completely satisfying explanation for why. Cold pools are exactly what they sound like. They're reservoirs of extremely cold air that sit over northern latitudes, typically anchored by high-pressure systems. Think of them as atmospheric batteries storing frigid temperature potential. When the pattern shifts and those pools get mobilized southward, they release their stored cold into the mid-latitudes. Normally, once you drain a cold pool, it takes time to rebuild. The air over the Arctic has to cool radiatively, which requires clear skies and long nights and minimal wind mixing. It's a slow process. But what's happening now is the cold pools are rebuilding on a time frame that seems impossibly fast. Forecasters are watching temperatures over central Canada crash back to 30, 40°C within days of the previous cold outbreak, as if someone hit a reset button. The anomaly here is the regeneration rate. Cold air shouldn't be able to recharge this quickly, unless there's some upstream mechanism continuously forcing the pattern into a cold production mode. Several plausible explanations exist, though none of them are fully confirmed. Persistent ridging and troughing patterns aloft can lock the jet stream into a configuration that repeatedly funnels cold air from the Arctic into Canada, like a conveyor belt that never stops running. Upstream wave forcing, where disturbances in the western Pacific or Siberia trigger downstream responses, could be reinforcing the pattern. Stratospheric coupling effects from earlier sudden stratospheric warming events might be lingering in ways that keep the polar vortex disrupted and the cold air pools active. All of these are within the realm of known atmospheric dynamics, but the speed and efficiency of the reload cycle is what's raising eyebrows. Here's where it gets particularly ominous. Forecasters are talking about two Arctic fronts, two distinct blasts of cold air merging into what some are calling a super blast. Arctic Front 1.0 swept through earlier, bringing sub-zero temperatures and lake-effect snow. Normally that would be the main event, the cold surge that dominates the headlines for a few days before things moderate. But Arctic Front 2.0 is already building over Canada, and instead of waiting for the first one to clear out completely, it's going to reinforce it. The two cold air masses are going to combine, creating a sustained period of extreme cold rather than the typical brief spike. This is not how these events usually unfold. Usually, you get one punch, then recovery. This is shaping up to be one punch followed immediately by a second punch before you can catch your breath. This changes everything about forecasting and preparation. Under a normal pattern, emergency managers can plan for a 3 to 5 day cold event. People can weather the storm, the cold moderates, infrastructure gets repaired, life returns to normal. But when you're dealing with a reloading pattern, the timeline extends to a week, maybe 10 days of sustained extreme cold, with multiple waves of precipitation and ice. That's when you start running into resource constraints. Utility crews get fatigued. Backup generators run out of fuel. Emergency shelters reach capacity. People who thought they could tough it out for a few days realize they're looking at a much longer duration event and they're not prepared for it. The atmosphere appears stuck, locked into a blocking pattern that's preventing the normal west to east progression of weather systems. Blocking patterns are a known phenomenon where high pressure gets anchored in place, forcing everything else to flow around it rather than through it. But the persistence of this particular block is unusual. Blocks typically last 5 to 10 days before breaking down. This one has been in place in various forms for weeks. Every time it looks like it might weaken, it reinforces. The jet stream keeps getting forced into the same exaggerated pattern, with a trough digging into the eastern United States and a ridge building over the western United States or Alaska. That pattern continuously funnels Arctic air southward while preventing moderating influences from breaking through. Meteorologists are using language that suggests heightened concern when they talk about repeatability. Phrases like extended cold siege and prolonged Arctic outbreak and multi-wave icing event are showing up in forecast discussions. This is survival language. This is the terminology forecasters use when they want to convey to emergency managers and the public that this isn't a typical winter storm. That preparation needs to be more extensive, that the impacts are going to be longer lasting and more severe than people might expect from looking at a simple temperature forecast. I need to enter a speculation lane here and be very clear about what's verified versus what's not. The reload behavior is real. The cold pool regeneration over Canada is observable in the data, but the reason for it is where things get murky. Some people, particularly those already suspicious of weather modification or climate engineering, look at this pattern and suspect external forcing or manipulation. They see the repeated waves, the precise timing, the way the moisture and the cold keep arriving in perfect synchronization, and they think it looks too organized to be natural. I want to emphasize there's no credible scientific proof of deliberate weather manipulation causing this event. None. But the pattern does feed distrust, especially among people who already believe geoengineering is happening. The atmosphere is behaving in a way that looks choreographed. And when natural systems behave in ways that seem too perfect, too aligned, people start asking questions that science can't always answer satisfactorily. What we can say definitively is that the cold over Canada keeps coming back, keeps reloading, and the mechanisms that normally dissipate these patterns aren't working. Whether that's purely natural variability, a consequence of larger climate shifts, or something else entirely, the practical effect is the same. The eastern United States is about to get hit repeatedly by Arctic air and moisture waves, and the reloading pattern means there's no clear end date to when conditions will finally improve. And the weirdest part is the trigger for all of this might not even be on this continent. This story may start in the Western Pacific, not North America. One of the most counterintuitive things about atmospheric science is that weather events thousands of miles apart can be causally connected. A typhoon in the Western Pacific can influence the jet stream pattern over North America 2 weeks later. A disturbance over Siberia can trigger a cold outbreak over Texas. The atmosphere doesn't respect political boundaries or even ocean basins. It's a single connected fluid system, and energy injected in one location propagates around the globe in ways that are only partially understood. Meteorologists call these long-distance connections teleconnections, and they're one of the reasons weather forecasting beyond about 7 days becomes so difficult. You can't just look at what's happening over your local region. You have to track wave patterns circling the entire northern hemisphere. The mechanism works like this. A strong convective system, say a major typhoon or a monsoon surge, releases enormous amounts of latent heat into the atmosphere.